I have the pleasure to speak also about the robust device identity, or why it matters so much for the security of the IoT infrastructure. I will not go towards identity-based encryption. However, it's important that the identity is robust, and there are a few other aspects which I think I can raise and contribute here. I will, in a first step, speak a bit about hardware security, why hardware security is so essential, because in principle, software can be circumvented by software. So that's, you need to keep this in mind. So when you build your security only in software, then another software is likely which can circumvent it. So a hardware trust anchor is important. Another aspect is then the chain of trust and the tool support for a chain of trust. Then I have a few slides on cryptography. Not to bother you, it will be short, don't worry. And then I will introduce a few basic services which are based on a robust device identity. And last but not least, a short summary. In the space of IoT devices, there are different hardware chip architectures out. These different architectures have either a crypto coprocessor assigned on the same piece of silicon. They have a separate crypto unit which calculates outside the standard MCU. There is the support of a complete security enclave with an own computing entity, which is you see typically in form of a secure element. Probably the most well-known secure element which every one of us has in the pocket is the SIM card. It's a separate secure environment for network authentication. So these architectures are in the market in different variants. The stronger the secure environment is shielded away from standard processing, the stronger typically the security is, but also the cost increases. And I think it was a few times already mentioned today that costs play an important role in IoT, especially with low-cost, large quantity devices. So these 20 billions will be not high-end mobile phones. These will be very cheap devices. So these 20 billion devices will have not a cost structure where you can add a secure element. So you need to look in secure solutions which are directly integrated in the silicon. Just to mention one, but there are others out. There's the famous ARM Trust Zone, but of course there are other ways to solve this also. In a RISC-V space, there are solutions out, for example, such as the Open Titan, which was recently launched from Google. So there are security enclaves currently coming more and more in the market, which is good because it underpins the software security by hardware. So now I have the pleasure to tell you a little bit what we are doing. We are de facto with our toolchain leveraging this hardware security enclave, whatever this hardware security enclave is, and bring it to a chain of trust to support the protection of the identity and the firmware. IR Systems, some of you might know this company because we are one of the largest tool supplier for embedded software development and IDEs. So whoever has developed embedded software probably came in contact with Embedded Workbench. We have since a few years enhanced Embedded Workbench with Embedded Trust, which is and C-Trust, which are security orchestration and security configuration tools. In principle, they influence the secure boot manager with a security profile. In this security profile, a device identity can be anchored. In this security profile, certain protection mechanisms can be anchored, such as encryption of the firmware. I will later comment when it comes to IP protection. And of course, the tools which you can see here on the left-hand side is one building block. Another building block which we have is Secure Deploy, which is a provisioning technology which does device individualization. In a tool, you develop the firmware for hundreds, thousands, millions of devices, and the individualization, the provisioning of individual devices with the production keys is then done with Secure Deploy. So the tool chain goes hand in hand with the provisioning technologies which we offer to the market. So this means we have a complete flow towards secure production from the tools. So in the development, in the test cycle, the secure boot manager, the whole system is orchestrated and verified, of course, with test keys. And then once the developer decides, okay, I'm fine with my firmware, I have ensured sufficient test coverage, it can be deployed. And during the deployment, during the manufacturing, the test keys are replaced by production keys, and these production keys can be chosen either group keys, but they can be also device individual keys, and the device individual keys form then a unique identity of each and every device. And of course, this plays then also a role in the lifecycle management of the device for an update. So in an update scenario, this cycle again is run through, and new firmware is created as new firmware is matched with the keys, with the profile of the boot manager, and then redeployed. So it's technology which of course can then leverage security enclaves to protect this key to a higher degree, to shield this key away from standard processing. But in principle, we as tool vendors want to support as many MCU types as possible to have security broadly available. That's one of our goals, making security with the tools available and offering an abstraction layer for the different hardware security enclaves which are on the chips. So embedded trust is the mentioned tool. So what we have integrated is an identity and certificate management, secure boot manager, and we can of course integrate this in the manufacturing line. By the way, one thing is interesting. In many cases, small devices have even the crypto capabilities to do onboard key generation. So the public-private key pair is directly generated on the device, which has a big advantage. The private key never leaves the device itself. Only the public key is registered outside. So I was a bit wondering before how IBE is doing this, but probably a discussion amongst experts later, because a private key is not good when it's sent around. A private key should stay in the device where it is. Just coming a bit to IBE sideline comment here. Nevertheless, we could do the same with IBE, so we are not based here on a PKI. In principle, we are to a high degree agnostic from key management. We are supporting with the tools what the customer wants. Now, I want to present you a little bit services which can be anchored into the profile of the boot manager, which can be anchored towards the device identity. Because our identity is nice, and the precondition for security, but it's not solving the security or secure communication per se. So you have heard before about secure communication. So an identity is the foundation to build additional services such as firmware IP protection, a remote attestation, proof of identity, firmware integrity checking, the whole update and lifecycle management, and also, of course, network and cloud integration. So I will show this a little bit how this looks in our development tools and our chain. There's a high risk of introducing backdoors. So this example here is taken from the mobile phone space where this incident happened. So a firmware image from a large OEM was modified on its way to the mobile phone hardware. So it was possible for a license manufacturer in Asia to sneak in backdoors, malicious code, into the image of the mobile phone of the Android build. It was in this case an Android OS. And then the OEM got back phones with pre-integrated backdoors without realizing that the phones he is shipping have some enhancements to the firmware which have been added by a hacker. Of course, something you definitely want to avoid as an OEM, that you don't get what you have delivered to your suppliers on the chips. So typically, the firmware is developed somewhere else where the chip is produced. So, and the OEM has to rely that the firmware, exact firmware what has been shipped ends up on the chip, which is is not happening always. Now we support this whole thing as follows. We can encrypt the firmware and we can manage with a digital signature that the firmware matches only with one boot manager running on one device. So in principle, with the individualization step, which we can do in production, we can modify the boot manager in such a way that a public key is there, and this public key checks a signature from the firmware image. The firmware can be an OS kernel with applications and services, and this public key, which never, by the way, leaves the premises of the OEM. So this key here, the private key, is generated in a secure environment, is used for signing, never leaves the OEM environment, and the corresponding public key, which can be shared, of course, because it's a public key, is then used for checking this firmware. So now, in case a hacker wants to modify something, will at the same moment the modification is applied, change the image, so the signature will match no longer, and in that moment our boot manager will refuse to boot the system. So a changed firmware cannot be brought up by the boot manager. Now you will ask, how do we avoid that the boot manager itself is changed? Of course, we anchor this boot manager in the security enclave of the chip, depending what the chip offers. So many topical smart controllers have different ways of secure boot. So for example, secure firmware management, so that it's possible to guarantee that this part cannot be modified and modifications of the other part can be identified. So a hacker has no chance to modify this firmware. In addition, we are able to do an encryption in a hybrid scheme so that even the firmware itself on the way to the device cannot be reverse engineered. And that's why we call it IP protection, because the intellectual property, which is in form of software buried into the applications, into the firmware, cannot be ripped off. And imagine when you see that, for example, artificial intelligence, machine learning, is deployed in many small MCUs, more and more the value of firmware continues. It costs a long time to do the learning for a machine learning system, so the firmware is getting more and more valuable, and we are protecting this value by IP protection. This is just one feature which we offer in conjunction with our software development tools. Other features which we offer is, or which can be built also by our customers, is, for example, a device identity proof. So in this case, it's a little bit different. The private key is on the device. It's not on the backend system. The private key is challenged with a random challenge in a challenge response way by an attestation service. A signature of the challenge is sent back, and the device itself can do a proof of identity. It's a very important thing when you want to figure out, is this the right device to which I'm sending my data? So the device identity proof, here it's catched, by the way, in a PKI structure, could be done in an identity-based system. It could be done in a symmetric key system, in a symmetric only key system. Then, of course, you need to keep the public key also protected a lot. But in principle, it's independent also from the used cryptography. Here it's a public-private scheme used. Others are possible. It's an essential thing to verify devices. Another thing is device integrity proof. The integrity tree, in principle, calculates a hash value over the relevant code parts, and then you can do a kind of remote attestation by signing this hash value with a private key, and then there's a signature check plus a check if the hash values of the application and the service are the correct ones, and only when they are correct, then the no changes have happened. So you have such features also in the mobile phone space. There are these runtime integrity checks on mobile phones which avoid that they are root locked, that they are hacked. So a mechanism which is on the mobile space already widely used. In the IoT space, it's more and more coming to have an integrity verification of the devices. Another mechanism which I want to share, which on a robust device identity can be built, is the classical TLS client authentication, which is used by many of the cloud providers. So when your IoT device authenticates to a cloud, typically a TLS client authentication is used. So a remote server requests the device to authenticate in a DLS session. It could be an AWS server. For example, we have recently launched Embedded Workbench, our tool environment for AWS cloud integration. This service is supported in conjunction with Embedded Trust here. So we can authenticate to AWS cloud in a TLS client handshake scenario. The necessary keys are already orchestrated and configured during the development of the device. The keys are anchored in our boot manager, and they can authenticate the device. And the big advantage here is not only a security advantage, it's a convenience and cost advantage because it's a zero-touch provisioning of the devices. So by orchestrating the connectivity of your device to the cloud already during development, you don't need later to touch the device again because the device has per se the right identity, which is known by the cloud. So all the cloud providers, by the way, which I know, support here PKI-based TLS server cloud authentication. So it's a pretty standard mechanism, which is in the TLS handshake procedure specified since many, many years. So we have not reinvented here a new system for the authentication purposes. This is widely rolled out, but we take care that the devices are pre-provisioned and that the later provisioning step is eliminated, which saves a lot of costs. Another way is you can use, of course, this TLS tunnel, which, by the way, also do many cloud providers, because cloud providers not only offer the possibility to upload data from the sensor, from the endpoint, cloud providers also offer maintenance, firmware updates, etc., and they do these things in a TLS tunnel. So the same mechanism as on the previous slide, but here the tunnel is used to change configurations of the devices, to change firmware parts of the devices, or update even the whole firmware. And what we take care again, we anchor the necessary authentication keys which correspond with the identity, with the certificate of the device in the boot manager already at a very, very early stage during development, which adds convenience in addition to security. Because the anchoring is done in a very low-level part in the hardware of the device, depending on the hardware support. So here we see a big convenience aspect. So quick summary, a robust device identity requires hardware support. Software security can be circumvented by software. The tools of IR systems and secured things support the seeding of this device identity in the toolchain during the device production at a very early stage. And by doing this, we can do a trust propagation to enable security services such as TLS authentication, remote device management, IP protection, and many other services are possible. I just presented you a few of them which we support. Thank you for your attention.